Hello everybody, this is Mr. Ray with our next calculus lesson. Uh, I'm basically renumbering all the lessons for this new version of the course. So the lesson numbers won't directly correlate to the lesson numbers on the actual lessons. So I'm just starting, we did lesson one, two, and three last week, and we're doing four, five, and six this week. So don't try to think this is not lesson four in our new schedule. This is actually lesson four of unit five. Okay. Um, so we're going to continue on with introduction to calculus. So we've looked at this lessons two and three. We're looking at the slope of a tangent. Okay, and we had a new way of looking at that. Um, Basically, we used a situation like this where if you want to know the slope of the tangent at a specific point, you basically uh, you act like you're taking a second point here, Q, but you're kind of moving Q along closer and closer to P till basically it's the same point, and you're taking the slope of the line between P and Q. So basically, by the time Q becomes P, that turns it into a tangent. Okay, instead of a secant. A secant is a line that goes through a curve twice. Okay. Um, so what we're going to do today, it's really the same topic, but slightly more application based and a different terminology. So we're talking about rates of change. Now, rate of change basically is a lot like the slope of a tangent in one circumstance. Um, Now, if you remember back to advanced functions, we did a fair bit of rates of change. When we looked at rates of change, there's two types of rates of change. There's instantaneous rate of change, and there's an average rate of change. Um, uh, when I taught this, I called this IROC, IROC, and this was AROC, AROC. So instantaneous rate of change, that really is the situation where you want to know how the dependent variable is changing with respect to the independent, how y is changing with respect to y at that very point, at that exact point. So this is a lot like the way we're going to do this now is we kind of simulated it in advanced functions. We took a point that was like 0.01 away and found the slope of that line, and basically it's really, really, really close to the slope of the tangent that would be there now. But in calculus, we're going to be more exact. We're going to find that exact rate of change at that point. Okay, so that's instantaneous rate of change. So that relates to basically the slope of the tangent at that point P. Okay, where we also are going to look at average rate of change. So average rate of change, it's always between 2 points. Measured between two values. How is it changing between those values? Whereas instantaneous, how is it changing at a very specific point? Okay, so you can relate the average rate of change. For example, if you're trying to find the rate of change, average rate of change between P and Q, this is where you basically draw a secant between P and Q and find its slope. So that would be delta S over H in this case. Okay, so it's kind of bringing back some things we learned in advanced functions and looking at from a calculus perspective. Okay, so we've talked about these three definitions. That should be review from advanced functions. Now, average velocity, we're going to be working with velocity here, but in terms of the application part. So it can be found the same way we found the slope of the secant. So it's the change in position divided by the change in time. Okay, and that will give you its speed, basically, like meters per second or miles per kilometers per hour, whatever. Now, here's an important connection back to vectors. So remember, velocity is a vector. So anytime you're asked for the velocity, which you are in this lesson, it's not just enough to say the rate of change is 3 meters per second. You also have to give direction as well. So this is a vector So be careful that you include both properties of that vector, that you're giving the direction and the speed, okay, in this perspective. Okay, instantaneous velocity, we've talked about this. It's a slope of the tangent. So at that one point of the graph, um, and it's found the same way we found the slope of the tangent. So the formula you're going to see here, um, down here, sorry, this is the velocity function at the point A, will be basically the value of the position at A plus H minus the position at A or over H, okay? So this is exactly what we were doing in the last two lessons, finding the slope of the tangent, okay? Whereas this here, you can see we're actually taking the two positions, we're subtracting them to get the change in position over the change in time, okay? So how far apart were these? So we divide by that. Okay, so this is really closely related to what we did in advanced functions, but it's relating it back to calculus. Okay, so if we go to the second page, we have some examples we're going to do. Okay, so you guys didn't have a vectors exam, so you probably won't relate to this question, but following the vectors exam, a textbook is dropped from a building 80 meters high. After t seconds, the textbook is s meters above the ground. So it's basically giving you the position based on the time of the textbook. Okay, so you can see at the beginning when time equals 0, the position would be 80, which is 80 meters above the ground, which is where it was dropped from, and then it decreases by 5t squared, where t is the number of seconds since it was dropped. Okay, so what we're going to do here are a few calculations. First one, calculate the average velocity of the textbook between 1 and 3 seconds. Okay, so this is average velocity, so it's the change in the position over the change in the time. This is like using a secant because you've got 2 points that you can calculate from here. So we're going to get the position at 1 second, the position at 3 seconds, and see how much both the position and the time have changed. So in this case, we've got, if we relate back to this function s of t, it's going to be s of 3 minus s of 1. So that basically means what was the position, what was the height at 3 seconds, subtract the height at 1 second. Okay, and then we look at, well, how much time elapsed? Well, that's 3 seconds minus 1 second. So this is like delta, the old delta y over delta x, except we're looking at s and t as our variables. So if we plug these in, if we plug 3 seconds in here, that's 80 minus 75. So s of 3, sorry, that's s of 3. Sorry, we want s of 1 first. No, we want s of 3. So that's 80 minus 75, so that's 5. Hold on, that's not right. So s of 3, that's, okay, sorry about that, that's 9. T squared is 9, so that's minus 45. 80 minus 45 is 35. Okay, so the position after 3 seconds was 35 meters above the ground. Then we subtract the position at 1 second, so that's just 80 minus 5, which is 75. And the time that elapsed was 2 seconds. So we subtract that, we get minus 40 over 2. Okay, and that's going to be minus 20. And we can put the units in here. So, we're dealing with basically velocity, so it's meters per second. So meters per second. Now, the minus sign here is actually telling you the direction, but we need to be more clear. So it's always good to write a little statement here. Average velocity is 20 meters per second and down, because that's what the minus sign means. The book is falling down. If it was a plus 20 meters per second, the position would be increasing. It'd be going higher in the air. Okay, but obviously anything falling, it's going down. So that's what the negative sign relates to. Okay, so that answers the question, the average velocity between 1 and 3 seconds. Now we're going to do the same question, but this time between 1 and 1.5 seconds. So again, delta S over delta T. So this time it's, instead of S of 3, it's S of 1 at 1.5 seconds minus S at 1, which we already did, over 1.5 seconds minus 1 second. Okay, now I'm just going to, when we plug in 1.5 into S of t, so S of 1.5, that's actually going to work out to 68.75. So basically the height of the book after 1.5 seconds is 68.75. And we already know S of 1, we did that in the last question. That's a height of 75. That was the height after 1 second. And then it's going to be a 0.5 second difference. And when we do the math here, we get negative 12.5 meters per second. But the negative sign, again, let's turn that into a word statement. Average velocity is 12.5 meters per second down. So the book is traveling down to the ground. Okay, and as soon as we put the word down, we don't have to include the negative sign because we've translated the negative into the direction. Okay, now C is basically saying explain why your answers for parts A and B are different. Well, this should be fairly obvious. When you drop a book, it's accelerating in speed the further it drops, right? So the average velocity will be changing on its way down. So between 1 and 3 seconds, well, basically, between, the part that we did include here, from 1.5 to 3 seconds, you will know that if you did that interval, that speed would be much higher than probably both of these separately. So overall, as the higher the time, or the more the time is, the faster the speed. Okay, so that's why these are different. So you could say that the book velocity will be changing due to acceleration, causing different velocities at different intervals. Okay, all right, so that answers that question. Another velocity question here. A toy rocket is launched straight up at, so the height S in meters. So this time we're shooting it up in the air. The height S in meters at time t in seconds is given by negative 5t squared plus 30t plus t. That's a quadratic, which makes sense because it's going up in the air, just like the book falling was also using a quadratic model due to gravity. What's the velocity of the rocket at 4 seconds? Okay, so they didn't actually say instantaneous velocity here, but the fact that they said that it's at this specific time, that means instantaneous. If it had said what's the speed over the interval, say between 3 and 4 seconds, that would be average velocity. So this is instantaneous velocity or instantaneous rate of change. So we're not using the same formula we did in example 1. We're going to be doing basically simulating the slope of the tangent like we did in the last lesson. Okay, so we're actually going to do the change in the speed. So I'm going to call the speed that we're measuring, so the velocity at 4 seconds. Okay, that's going to be equal to, now you'll see this looks very familiar from last lesson, the limit as h approaches 0 of s of 4 plus h minus s at 4 over h. Okay, so you can see the 4 is used in both. This would be like your point Q, which is h units away from 4 seconds, but we're basically making h approach 0. So basically this becomes instantaneous speed or slope of the tangent at this point. Okay, so you can see s of 4 plus h is basically replacing t with 4 plus h. So I'm going to calculate that over here in a side calculation. So basically everywhere we see a t, we change it to 4 plus h. So negative 5, 4 plus h squared plus 30t, so t changes to 4 plus h, and then plus 2. Okay, so I'm not going to do all the intermediate calculations here. This actually works out to minus 5h squared minus 10h plus 42. Okay, so I'm basically going to replace this s of 4 plus h with that. Don't forget to put the limit at the beginning. It's very easy to forget. So minus 5h squared minus 10h plus 42 minus s of 4. So s of 4, we actually know what it is. It's going to be 42. If you plug in 4 into this calculation, s of 4 is 42, which you can see it's actually in both equations. This is going to be the difference between the 2 points. So when I put the 42 there, you can see that this cancels out very nicely. You can also see that I can factor out an h from the 2 remaining terms. So this becomes the limit as h approaches 0. That divided out becomes minus 5h. That divided out becomes minus 10. And now at this point, we can safely plug in h equals 0 as it approaches 0. So this whole term becomes 0. So it's basically minus 10, just what's left over. So v at 4 seconds is negative 10. And now in terms of unit, the velocity would be meters per second. And now let's make a written conclusion. Therefore, the velocity of the toy, I'm sorry, I guess that was out of the picture there for a while. The velocity of the toy is 10 meters per second going down. Now this is an interesting one because it sort of depends, like if this toy rocket is launched in the air, the velocity won't always be going in a downward direction. It's going to be going up until it reaches the vertex, at which point after that, as it starts falling to the ground, it'll be going down. So this isn't an assumed thing that it's always going to be negative like the book was. The book was dropped in the previous example. So at every velocity from the time it was dropped to the time it landed on the ground, every velocity will be going down, whereas this one depends. For example, if we found the instantaneous velocity at 0.5 seconds instead of 4, that's probably still on its upward path. Okay, so just don't assume that it's always going to be negative based on these examples. It depends on where in the path we're talking about. Okay, so there's 2 examples of instantaneous velocity and average velocity, which are rates of change. So here's our formal rate of change and velocity definitions, which we've already used. So just put them here so you have something to refer to. This one's probably the most important one. This has to do with the rate of change at a specific time, which makes it instantaneous. And you can see here that this formula is pretty much exactly the same formula that we used when we did slope of a tangent. So you can see how instantaneous rate of change relates directly to the slope of a tangent, where the average rate of change is the slope between 2 points, between 2 times. Okay, so you notice we don't have any limits here because we don't have to pretend that something's approaching 0. We can just look at the values at those 2 points. Where this, we have to simulate 2 points where one point is approaching the other point. Okay, so one last example here. This one will be a little bit trickier. The total cost in dollars of manufacturing X calculators is given by this. This is like a cost function. The cost based on X. X is the number of calculators that are being manufactured. So the cost will be this formula, 10 root X plus 1,000. Okay, so the first part is basically using the formula. There's nothing about rate of change in the first question. What is the total cost of manufacturing 100 calculators? So that's simply C of 100 is equal to 10, and then we take the square root of 100 plus 1,000. So this is, you could do this in your head. Square root of 100 is 10. 10 times 10 is 100 plus 1,000. So that's $1,100. So it costs them $1,100 to make 100 calculators. Okay, so part B is what is the rate of change in the total cost with respect to the number of calculators X being produced when X is 100. So we're trying to find the rate of change. How fast is the cost changing at the 100th calculator? That's basically what that's. So that's the fact that we're only looking at one value and not a range of values. This is instantaneous rate of change. Instantaneous rate of change, or as I referred to earlier, IROC. And the other one would be AROC because it's average instead of instantaneous. Okay, so when we do this, we're going to set this up to be, I'm going to do 2 columns here for the calculation. So this will be the limit because instantaneous rate of change uses the limit. And that's going to be the limit of C of 100 plus H minus C of 100 over, again, it's going to be the change, which will be H, basically 100 plus H minus 100. Okay, so now we actually have to use our equation, our formula for the cost. So this is equal to the limit as H approaches 0. So all we really have to do here is plug in, instead of wherever we see an X, it's going to be 100 plus H, so that's going to be 10 root 100 plus H. And that's going to be plus 1,000. So that's still part of the C of 100 plus H. So that whole thing there, that's C of 100 plus H. And then we subtract C of 100, which we already calculated above here. That's going to be 1,100. And this is all over H. So you can see we don't really need the brackets. I just put them there to show you this comes from C of 100 plus H. So I can subtract these two numbers. So I'm going to have limit as H approaches 0 of 10 root 100 plus H. and this was going to be working out to minus 100 over h. Okay, so this looks kind of nasty, but remember our strategy from last lesson. What we're going to do is rationalize the numerator. So we're going to multiply this whole thing by the conjugate of the numerator, which is 10, 100 plus h. Now remember, when we take the conjugate, we're not worrying about signs in here. We just flip this negative sign or minus sign to a plus, like that. And same thing on the bottom. Plus h plus 100. Okay, got room for one more line here. So limit as h approaches 0. Okay, so whenever you do this rationalizing, you always end up with basically a difference of squares, because this is sort of like a minus b and this is a plus b, so the result is a squared minus b squared. So what we're going to get here, I'm basically squaring this term here. So when I square this term, it's going to be let's see, it's going to be 100. So I square the 10, I get 100. I square this, I get 100 plus h. Sorry for my writing. And then the second part will be minus this squared. So this squared is going to be 10,000 over h. I guess I got room for one more line. Limit as h approaches 0. Hopefully you can see this. Let's just get it up a little higher. Okay, so if we multiply 100 with 100, we're going to get 10,000 again. So 10,000 plus 100h minus 10,000 over h. And so this has actually worked out really nicely, because the two 10,000s cancel each other out. No, I did forget to multiply the denominator, so let's put that in. It's never going to work out that nicely. 10 root 100 plus h plus 100 on the bottom. Now I'm going to leave it like, I'm not going to distribute it, and you know why, because I want to cancel the h. So that's going to be h 10 100 plus h plus 100. Okay, so you can see that these have canceled out. I can cancel that h, which is all that's left, with that h. And I'm going to continue up here. I've got limit h approaches 0. So what do I have left up here? I've got basically got my 100 on the top. Everything else, those two terms are gone. That h cancel with that h. And on the bottom, I've got 10 root 100 plus h plus 100. Okay. Now you can see up to this point, like any of these steps before, I could not substitute in h equals 0, because that would make the denominator 0. But now that I've canceled that h, I still have an h on the bottom here, but if I plug in a 0 there, that's okay, because that turns into root 100, which is 10, and that's totally good. Okay, so let's actually plug that in now. So if I plug that in, I get 100 on the top, and this, like we said, that's a 0. So that's root 100, which is 10. 10 times 10 is 100. And then this 100 plus that 100 is 200. Well, that's simplified quite nicely. So this works out to 0.5, or 1/2. Now, what are the units here? Well, it's the change in the cost for the 100th calculator. Okay, so that turns into dollars, and it's per calculator. And that's our answer. So the rate of change in the total cost is, now it is a plus, okay, so it's actually still increasing. So the rate of change is positive, but it's going up by 50 cents or $0.50 per calculator, okay? So if you notice, I've got a few questions to try out. The solutions will be posted, so try a few as you go. Make sure you can do that. Next week, we're going to finish off the introduction to calculus. So you will be getting a new assignment. Well, this is Thursday that I'm uploading this lesson. There'll be an assignment at 3 o'clock tomorrow, which will be the 24th, and that will be due Sunday at midnight. There still will be another bonus of 5% if you can get it in by 8 p.m. Okay, so hopefully this makes sense to you. It's really just applying what we did with some, some application type questions with velocity and rates of change. So instantaneous rates of change relates to the slope of the tangent, and average rate of change relates to the slope of the secant. So that ties in nicely to what you did in advanced functions. Okay, so thank you very much, and don't forget about the assignment that will be due at the end of the weekend. Okay, have a good day.